So let me first set the proper expectation for the paper. So this is one of the reviews that I got. So as you can see that this paper is neither properly a functional Perl, nor functional, nor logical. I should confess that when I got this review, I was elated because that, I guess, subconsciously that or semi-consciously that has been always my intention. And I was glad that it showed. If the reviewer sees that, I want to say thank you. So what was it about? Let's consider summing an array. Well, when you hear a summing array, probably many of them imagine something like that. Or maybe something like that, depending whether you're leaning functional or imperative. These are just two different ways of saying exactly the same thing, and with a good compiler, it would compile to identical machine. Ideally, though, when one hears summing an array, one should think of this. And there are some programming languages that can actually let you say exactly like array. So, but you can always write another language. And this is what Guy Steele in his keynote in SAP 2009 advocated. So why is this thing is better? Well, first of all, it tells us what needs to be done, just summing the array, but not how. And the best thing, there are many of those hows. For example, we can sum array like that, associating to the left. This is the code that we saw at the beginning, right? Or we can do it in a different way. So for example, we can split the sequence, we can split array into parts, or more parts, not necessarily equal, and sum them separately and tally up the results. As you can see, the parts of the array which are allocated here, they're completely independent, right? So we can allocate, the summation can be done by different processors, and this processor would not only would have not have any write conflicts because there is no shared memory. There is no read conflicts because they are not reading the same elements. So they can be done completely in parallel. So that's called embarrassing parallel because, well, it's so good that it's just embarrassing. So which of those methods you choose? Well, it depends on, I guess, and this is very good for GPUs because all of them, there are many processors and all can do exactly the same work, summing better. So which of those we can choose? Well, it depends on the problem. So if you have a big enough array, that's what bothering with parallelizing, or if you have how many CPUs you have and how big NVIDIA GPU you can afford. So why did it work? Well, I mean, why did this embarrassing parallelism came in? Well, because plus is an associative operation. That's why we can group arbitrarily. And there's also 0 because we can initialize the kinlet. So set with an associative operation. And 0 is called mod. And another thing that one should not forget is the efficiency. That operation takes constant space and constant time. Well, besides this, plus there are many more monoids. For example, there's integers with a multiplication. And one that's also possible. Right, and order sets with a moving operation, and maximum element is also then. Other monoids, for example, there is a set of functions from one to another, where the operation is compositional and identity is the unitary. There's also it's generally not efficient because, well, it depends. These are mathematical functions. Depends how you represent a mathematical function, but it's in a programming language function. And this is a programming function, composition function. Composition might take constant time, but the result would not be constant space, right? Because it includes both reference. Another well-known monoid is the list or sequence, where the operation is the concatenation. Well, if it's in a list, it's neither, space nor time efficient because concatenation takes, as we saw before, time, and it definitely takes a linear amount of space. Okay, so coming back to our summation, so we know if we have some elements of the array, then we can do it embarrassing part. That's so trivial. That's well, what if there is a minus? We'll replace all pluses with minuses. Well, minus is not associative expression, right? So when they replace, we need to specify how we're going to group them. So we can group them from the left, or we can group from the right, or maybe some other way. Well, it's perhaps maybe a little bit less trivial to know that both of those can also be done in embarrassing file. And I encourage you to think about how you can implement both of them in parseling file. It's not that difficult, and as a hint, I tell that one of them is much easier than the other. So in the paper, there are 3 more examples of less than obvious monoids. And the paper is meant to be kind of a half tutorial, so it explains lots of stuff regarding monoids. And well, this talk should have been, well, I mean, ideally it would have been as a tutorial, but unfortunately I don't have time for that. And I said full paper because in the paper which is on my website, because it contains, well, more stuff that I could squeeze into the official proceedings. And it also has exercises and some codes. So if you be interested in reading the paper, then I mean the full paper would be advisable. So the paper is written in mathematical notation, so it means the Greek letters with lots of subscripts and superscripts. But it has a useful notation. So it can be implementable, translatable into code. And there are implementations. There is a common implementation, both functional and imperative implementation. Then recently, Martin Elsman has looked at the paper, edited it, and implemented it in FootHark. So FootHark is a rate processing language, mainly intended for compiling into GPU, but I think it's also can be multi-processing. So everything that's in the paper actually can be run on GPU. Actually has to run. So let me first say a few things about things that I'm not going to say anything more. So this is one of the examples in the paper, which I would not talk about. So the example is from Advent of the code 2022. So we have this file that contains numbers or digits separated by commas and further separated by bars. So the question is, the task is to sum numbers which is separated by commas, and of those groups separated by bars, find the maps. So this is the typical data analytics problem, data aggregation problem. Right. And so we can either have a streaming solution, so they read this character by character and accumulate the results when we finish this data in the final. So again, without first splitting by bars, just reading strictly character by character. Or we can have embarrassingly parallel solution. So we suppose it's a big file, we can split the file by the pages, or to a map, for example, we read split file with pages, and we don't know and give the pages to a set of pages to work. And we don't know where the page boundary lies. So page boundary makes cut numbers or can cut before the delimiters. We don't know at all. And still it can be done. So each workers could work in parallel without communicating at all with each other, without snooping on the neighbors, and eventually we can tally up the results. And it all can be done, well, there is it's actually in the rest of it, and you didn't. It all can be done through the, well, it all works because of the monoid. I think it actually doesn't. Okay. Still. Oh, I'll say what's something I'm missing there. Okay. So this is a very practical problem of data analytics. So suppose this is a JSON file and you're doing some kind of aggregation on this file in memory without parsing it, without loading. So that's one of the practical applications. And it's described a little bit in the paper. But what I want to talk about in the remaining time is a, well, maybe less practical application, but I think it's a tutor. It's a Boyer-Moyer majority algorithm. I don't know how many of you know this. It's rather relatively old algorithm. The task is find a majority of the sequence. So we get a sequence of elements and find the element that occurs more than half, strictly more than half of the time. So the majority is presumed exists. So the interesting part of the algorithm that it operates on constant space and time. In space, it might be surprising because majority is the global property, right? You kind of used to know, how many and which. So although we presume exists that majority exists, we don't know which element. So that's, so we kind of have to, to predict it. But how can we do it in only constant space? There isn't seems to be enough space to accumulate it. So if we don't know if majority exists, so if majority doesn't exist, the algorithm returns just random element. So if you generally need to have a special second pass to verify that found element is a majority if you are not sure if it exists. That pass might not be necessary depending on the problem. So what is the algorithm? What I show, it's a little bit more generalized algorithm than Boyer-Moyer, but so the working data structure is the element and the count. So it's really constant space. So there is element, some element, and the count of both sides. Here how we merge these two data structures. So if the count is 0, then we ignore that we take other element. If the elements which are merged are the same, the candidate votes will add those counts. And if the count elements are different, then the winner remains, and we subtract. So that's how the algorithm works. And it's probably easier to see on example how. Suppose we have sequence A, B, C, and so this is the data structure for the count. There is one vote for A, one vote for D, etc., etc. If we merge this according to algorithm, then A and B different, then the count goes to 0. But we now merge after this the second element, well, because it's 0. This makes. Now if we add second, well, C now the same, so we increase the count, and at the end, that's works. Let's define the results. This is how the algorithm was proposed. So just do it sequential left to right. And actually it was a little bit specialized for the sequential. So that's what the original. Well, let's try to do it a little bit differently. So before I started, I merged this series and then merge, so left to right. Let's start first, merge one B and one C, right? So it would be B and C different, that's what we get. And then if we merge one and A, we get this. Note something? They're different, right? So the operation is not associated. And if we do exactly the same dance later on, that's well, no surprise here, right? I mean, do stupid thing, then get stupid result. The operation is non-associative. If you do reduction with an associative algorithm, and then the result, of course, depends on the strategy. Let's say it's kind of non-deterministic for so, right? It's not defined. Well, as I said, that original algorithm is not associated, and in literature it's called prototypical serial algorithm. So you really have to do it right because it. But yeah, although this structure is different from this structure, but you can see that the count in both cases is greater than 1. And the C is also the same. And in both cases, it's a majority. So it's kind of what, I mean, it seems that the algorithm could work in parallel, right? Although it's not precisely associative, although it's not precisely that the right thing, but seems to be the result is correct. could be correct. How can we be sure? Well, that's what within the remaining times I would show. Okay. Okay, so let's first start from the very beginning. So how do we define majority, how compute majority that obviously correct? Well, I mean, we just get elements from the beginning to the end and put them in a bucket. And at the end, find element with the highest count. Right? So this is exactly equivalent to what not with this. It has a majority that element has count, obviously. So it's obviously correct. So let's consider a particular representation of the multiset. So it is a set of or multiset of mismatched pairs. So mismatched pair, I mean first and second pairs. And well, once we kind of group, so we partition of the partition multiset mismatched pairs, then there may be left over, right? Some element which cannot be packaged. So this M ordinal out, and K is the count situation. And here are the examples. For example, we have this multiset. Example, it can be partitioned A part C, B part where was C, and well, C is remaining, and with or we can find a pair of A and B's and then C's. So the representation is not union. Right. Okay. Then once we say, well, this is a representation of a multiset, it's kind of natural to define what the function declaration that says what multiset it is a representation of. Right? And it's easy to define. You just look at all the elements that occurs and just collect them. Well, the original algorithm I said multiset, right? Says accumulating a sequence and take the largest of. So now we need to think about how we can do operations, accumulate, take the largest element onto this particular representation. Can we do it? Well, let's start. I mean, another thing. How can we have this structure? How can we merge them? Well, there's a set of pairs, and when we merge, well, obviously we should merge those set of pairs. M1 is the same, we count the votes, this stands out. An interesting case is this. So if M1 and M2 are distinct, well, if they're distinct, we can pair them up, right? We can pair them up and with a set of multiple pairs, and what's remains with the remaining count. Well, interesting thing about it. That is, well, I said it's a multiset union source. So that's how to do multiset union on this representation. And it's morally a multiset union. What does it mean morally? So if we take a multiset of that, found this result, then it's a multiset union of multiset operations. Why is it true? Well, it's easy because if you look at the equations, we never discard anything and never duplicate it, right? Everything that's from the arguments got in the result without duplication. Obviously, that all elements that are counted to. So that's obviously. This is a very, very good relation that actually has a special name, but I won't talk about the name and just show why is it so useful. Well, because this operation is obviously non-associative, right? Because you probably see that it looks very closely to the original one, and that wasn't associative. But if we use this equivalence relation that says 2p1 and 2 equivalent if considered as multisets, like the same, then this is the hold up to this equivalence. Why it holds well? I mean, according to the separation, it converts all p's into multiset, right? And multiset union is so it's also it's a good so P representation is actually monoids, morally monoid, modulo this operation. Yes.
So what is the magnitude population?
So it's you just, I mean, accumulate, take all of this from the multiset, and that's what it would be.
Thank you.
Okay. So we know that P is a monoid, more or less, given this approach. But it has, so we kind of figure out the simulation part. Now we take a part of finding that. And it has an interesting problem. So if this multisets has a majority, then C is greater than 0, and M is the majority. Well, why is this true? Well, P is the set of multiset pairs. Mismatch pair. I mean, second component is not equal. First component is not second. But the same element may occur not within the same pair, but across the different site multiplication. But none of those elements that occurs more than half of the time. Why? If it occurs more than half of the time, by pigeonhole principle, there would be one pair that has two equal elements. And the construction P cannot have pairs with equal. So if this multiset has a majority, then it has to be. There's no choice. One of the corollary of that is that if the multiset has a majority and it's equal to some other multiset, then it must be that M and M prime is the same and counters are greater than 0. They don't have to be the same counters, but they both greater than 0 and M. So the properties, you can say that this equivalence relation not only makes P a monoid, but it's respectful of majority. The one of the. So that gives a kind of well, precise definition what we the intuition we initially had. All kind of the same, but preserve the majority. Now we say what exactly that means for this. And this gives the algorithm parallel Boyer more. First perform the monoids reduction in terms of this presentation and take M. So, and it's just that the correctness justified that. But somebody said, well, wait a minute. Well, although it is monoid, but is it efficient? Well, P is the multiset of all elements we accumulate, right? So keep accumulating elements, so it's not constant space. Yeah, indeed, it is. But eventually, we only need M and not maybe C. We don't actually care about it. We only care about it. And look at like questions. How do we, compute this M? Well, we do case distinction, but case distinction uses only M and C. And only computation of M and C includes M and C. So the P doesn't actually enter the computation. Right, so, well, if it's not useful for final result, then we might as well not do that. And if we drop this P, well, we ended up with growth originally. So it's kind of anticlimactic result. I'm sorry. So we didn't derive anything new. We derived what we started. Well, as a consolation, what we gain is that we now know that it works. That intimation that Boyer more algorithm can be done in parallel, there was at least one person had this intimation that can be done in parallel. But he also was aware that it's not associated, and he wasn't aware didn't know how to predict the record. So there wasn't any, there was intuition and vague feeling, but there wasn't any assurance. Now we can assure that it actually works. Okay, so it's time to came to the conclusion, and for the conclusion, I borrowed the slide from Guy Steele's essay, the keynote, who emphasized the associative inventing efficient social operation is a big thing. The emphasis is this slide. The Guy Steele isn't a very emotional person. Well, It's really big. Yeah. Well, and keeping in title with the title of the paper, so there are more conclusions. First of all, there is more to the social theory. And so different kinds of and more, well, not that all of them matches sameness, identity, but there is a different kind of quality which could be used. And as to the proof methods, there is more than a induction. Looks like, for example, in types and programming language, that when that the only thing that teaches induction. That would show. I was proud that I never use induction. Use pushing for principle. And well, I mean, I know there is one more thing. I mean, I'm not speaking from thoughts. So, so before thinking of something true, think we could